said, these desks are very obviously not 6 feet apart anymore. Would you mind moving backward? I'm sorry, I don't know anybody's names, and even if I did, I can't tell who you are with this. And you four right here, can you kind of like space out a little bit? I just want to make sure that we're being doing the best we can here. The desks have definitely moved around. Okay, might be here for anything. And let's see. Okay, does anybody have any questions before we get started? Or comments or concerns or anything? Okay, I'll take that as a no. So where did we leave off last time? We introduced the concept of a matrix. And from one point of view, let's say point of view. From one point of view, this is just a rectangular grid of numbers. We made an implicit assumption about what we mean by numbers, real numbers. And yeah, so we can manipulate this thing as numbers. So another point of view, or where do these come from? So these come from a system of linear equations. So some number of equations with some number of common variables that are common to all the equations. Okay. An example. 1, 2, 3, 4, 5, 6. This would have been a matrix. This comes from, if this comes from, okay, if this is interpreted as the system x1 plus 2x2 equals 3, 4x1 plus 5x2 equals 6. Then we think of this as the augmented matrix. So this is the augmented matrix representing that system. Okay. And all of the things that we would have done to solve this system, we could represent as just manipulating the numbers in this matrix, right? And so we had these special operations. I'm going to give these a name. Just they're called row operations. Okay, so the first one that we can do, the book has specific names for this, and I wanted to use the same names as the book. These are not special technical terms, these are just what the book has chosen, and probably other books choose too. The first one is replacement. And this one is when we take one row and we replace it with that row plus some multiple of another row. Right? Maybe I should write that out. Replacement of one row plus a multiple And we convinced ourselves that this doesn't change the solutions of the equation. So the corresponding equation, we still get the same solutions. Nothing has changed in that way. Number 2, what we'll call this one. Transposition, interchange. Replacement, interchange. Two rows. This is one that I actually left out last time, but it's also obvious that this doesn't change the solutions of the system, right? If we just swap 2 rows, all we've done is change the order in which we're specifying the equations in the system. That doesn't change the solutions. Okay. And number 3, I believe it's just called multiplication. Scaling. Over 3. Scaling. Of a row by some, and I'm going to use the technical term for this. This is a very common technical term. By some scalar, some real number that I multiply by the whole row by. Okay. Now, let's do an example of this. This matrix here. 1, 2, 3, 4, 5, 6. What I will do is I will do a row operation of replacement. Write a little R above the arrow there to indicate that I'm doing replacement. The replacement I'm going to do is I'm going to add to this bottom row -4 times this top row. So the top row is unchanged by this operation. The bottom row of the second row becomes 4 minus 4, 5 minus 8, and 6 minus 12. 6. Okay. So this is an example of doing that. And what is the resulting system of equations? x1 plus 2, x2 plus 3, no, what am I saying? 2x2 equals 3. And then minus 3x2 equals minus 6. And we see we're now in a position where we can get the solution to this. Okay. So that's just an example of the row operation. Now, I want to give a term to this relationship between these two. What will I call this? Row equivalent. Okay, so 2 matrices are equivalent if you can get one by row operation put us in parentheses. We only did one operation here, but we could do a series of operations by row operations on another. Now this is just a technical term for, this is just a term that we're using to describe the fact that, we should say this, fact. Two row equivalent matrices which represent a system of equations. Okay, so two augmented matrices, two matrices that represent a system of equations like this one does. Have the same solution. So if something is a solution to one, it's a solution to the other. If one of them has no solutions and the other one doesn't have any solutions either. And we know this just based on the fact that each of these row operations, it doesn't change the solutions. Okay. So a few properties about this row equivalence of matrices. Okay, so the first one is, I'm going to use some notation, and I'm going to explain it. Okay, so I'm going to write in here the matrix A is row equivalent to the matrix B. Now I'm using a convention here. The convention is, maybe I'll put this over here in the corner of the board. The conventions are just there for the convenience of communicating ideas to someone else. It makes it easy if we're talking the same language. And the convention that we use is that capital letters, is it A? Capital, do you spell it with an A or an O? Capital with an O is the building. Okay. Capital letters represent matrices. And then, well, we'll just leave it at that for now. Okay, so this is a matrix, and this tilde I've written in between says they're equivalent. So, if A is equivalent to B, and B is equivalent to A. Seems almost obvious, right? What am I saying whenever I write this? I'm saying that if I do a series of row operations on a matrix, I do some replacements and I do some interchanges and I do some replacements and I do some scalings and I get a new matrix, I could go backwards. I could undo all of those operations, right, and get back to the original one. So row operations going in this direction, there are also row operations that I can use to go in the opposite direction, to go back to the original matrix. Okay. This is a kind of symmetry. If A is equivalent to B, then B is equivalent to A. Which is what we expect from calling something equivalent. Okay. If then. Okay. Second property. If A is equivalent to B, B is equivalent to C, then A is equivalent to C. Saying something again seems fairly obvious, right? If I do row operations to get from A to B, and then I do a series of row operations to get from B to C, then I can just do all the operations one after the other and get from A to C. Right? Okay, this is a kind of a transitive property of this equivalence. And finally, the most obvious one of all, every matrix is equivalent to itself. Another convention. Tilde means equivalent. So these are just some basic properties of this row equivalence. The most important one to us is that if it represents a system of equations, then we didn't change the solutions to the equation. What we're hoping for is that we take a matrix, and maybe it's not obvious what the solutions are. We can do a series of row operations, and it becomes a matrix, a row equivalent matrix, so it has the same solution. that's much easier to see what the solutions are, like this one. Right, we get x2 immediately is equal to 2, and then if we were to plug 2 back in here, subtract to the other side, we would get. Okay, any questions at this point? Good. So, how do we use this? The way we're going to use this, and I'm going to try to do this through an example. The way we're going to use this is we're going to apply row operations to get a special form. How should I say this? To get our matrix into a special form. Okay? So I'm going to do this by way of an example. Yeah, let's do the example first, and then I'll kind of give you the terminology as we go. So I'm going to use the same one as the book. And as we work our way through this, I'll tell you what the book calls all these things. But what we're really doing is using them, right? On the exam, if I ask you a question like, what is the pivot column, or something like that, you'll be able to tell me, but that only tells me you've memorized the definition, right? So what we're really interested in is actually using this stuff. But if we want to talk to each other about it, we need to know the names for the things. Okay. So let's start with a matrix. Oh, is this a large matrix? I think it's okay. We're writing out by hand anyway. Let's start with, let's go column by column. The first column is 0, -1, -2, 1. The second one is, and like I mentioned last time, I'm using examples directly from the book, not entirely because I'm lazy, but because people who are following along at home can't really see anything through this camera. So if they want to go along with the examples, they can just look in the book. Now, also, as I said at the beginning of the class, I really do recommend, actually I'm going to kind of demand, that you read the section in the book, right? I really would like for you to be coming to class with questions. It's fun for me to just stand up here and just talk and talk, but I'd rather know what you want to know as opposed to me just talking. Listening to the sound of my voice. Okay. That, and the final column, 1, -1, -7. So we could think of this as a system of 4 equations in 1, 2, 3, 4, 5 unknowns. This is, by the way, as we were talking about last time, a 4, 5, 5 matrix. And we know what the row operations are. We've internalized this as far as reason. Example. We're ready for a larger example. Okay. So the way that we're going to do this, the way that we're going to introduce this algorithm, we're going column by column. So we're working our way from left to right and from top to bottom to get this into this special form. We'll see at the end what's so special about it. Let me pause for just a second. Does anybody have any questions? Okay, so the first thing we do is we start at the first column, and we call this a pivot column. What does that mean? It means the column contains a pivot. I'm just using words and I haven't defined them yet. Well, what does this mean? It means that this entry in the matrix is the one that we're going to use through row operations to eliminate the things below it. Okay. Now we have a problem. What's the problem? Yeah, it's 0. I can't use 0 to eliminate anything. So the first thing I'm going to do is, let's say, pivot starts as top leftmost entry. Okay. What can I do to get rid of this 0?
Change it with the fourth equation or the fourth equation?
The fourth equation would be perfect, as we put a 1 right there, and it's really easy to see how to eliminate everything with 1. Yeah. So, perform or more. You see what I'm talking about? I do this all the time. Okay. Perform, this should probably be a capital P. Perform a interchange let's change this statement slightly. Starts as top leftmost entry of a non-zero column. I noticed a possible problem here, which is that if everything in this column was 0, we wouldn't be able to interchange anything. Okay. So let's start from the column with no zeros in it. It's, in this case, the leftmost one. Form and interchange. An interchange row operation, if necessary, we make pivot non-zero. Okay. So that's what I'm going to do. My first operation is going to be, I'm writing an I here just to signify that it's an interchange. And I'm going to do the interchange that you suggested. Someone suggested, I think. Okay. Which is, this is a pain. I need to write this on the board. Should be PowerPoint for something like that. Okay. And minus 1, minus 2, 1, 3, 1. Minus 1, minus 0, minus 3, minus 6, 4, and 9. Okay. So here's our new matrix. Row equivalent to the one before. I'll get more of a problem because I'm going to write this again. All right. Next. Use pivot. Use pivot to eliminate all non-zero entries below. So step 2, we're going to use this to get rid of everything below it. Okay. I guess what I'm going to do is I'm going to, this is still my pivot. The pivot is the location in the matrix. So we're referring to that as being the pivot location. I'll put it in the same spot here. So the top row stays the same. 7. Okay, now I'm simply going to add this row to this one. That will make this a 0. So 0, 2, 4, minus 6, minus 6, unless I made a mistake. Taking your silence as agreement. Okay, now I'm going to add double this row to this row. So that'll make this a 2, 2 minus 2 is 0, 8 minus 3 is 5, 10 minus 0 is 10, negative 18 plus 3 is 15, and negative 14 minus 1, negative 15. Okay, and the last row already has 0, so we don't need to do anything. All right. Now, next step is, in the book they say cover up this row. Ignore the row pivot that we just used. I'm using my own words to describe this. The book probably describes it differently, but no one will accuse me of just reading from the book. Okay. Okay. And then finally, go to step 1. So we go back to this one. We have decided that this row is finished. This row is finished. And so now I go back and I say the pivot is the leftmost, the top leftmost entry of a non-zero column. Well, now this is a 0 column. This one is not. And so 2 will be my new pivot. Okay? And now the math gets a lot harder.
Second and third equation. So he said we're not.
So this one is just 5 halves times this one. Okay. That's probably why they included that in this example.
I do have a question about that. So since they are the same, would it even be necessary to have the third one? Like a third equation?
Well, so what we have found, we see in the previous iteration of this, these two were the equations that corresponded to these, or these two rows were the ones that corresponded to these two, right? Previously, they were not, well, we say the same. One is a multiple of the other, right? So at this point in our algorithm, we didn't know that one of these equations was unnecessary, right? It wasn't obvious. Whereas once we get to this point, we see that we can eliminate this. Well, let's do this, actually. So the next step, I should have said that was a replacement. We'll do a replacement. We'll do this elimination, and then we'll talk about the consequences of it. So the next replacement, top row stays the same. Second row becomes 0, positive 2, 4, minus 6, minus 6. This is my pivot. And this row did change. I guess it's not so bad. So 5, 10, minus 15, minus 15. And now, 0. And now we can perform a replacement here the the one that you suggested, which is multiply this one by -5/2 and add to this one. Okay, so I'll divide every entry by 2, multiply by -5, and add them together. What do I get? I get that this one becomes 0. 4 divided by 2 is 10 times 5, or 10. You know what I mean. This becomes a -10. This becomes a -15, and this becomes a negative, or this becomes 15, and this becomes 15. And so we end up eliminating this entire row. Yeah, what we found is that our, one of our conditions was redundant, that it was actually equal to some multiples of the other ones added together. Well, what about this row, this bottom row? Let's see. So if we multiply this by 3/2, we get 0. 3/2, we get a 6, so this is 0. So 3/2, this is -9. Half of -6 is -3, times 3 is -9, plus 4, -5. And finally, 3/2 of -6, -9 again. Okay. Now, we have entirely eliminated this row. The algorithm doesn't say to do anything at this point, but what we're going to do is we're going to say we're done with row 2 and just follow the steps. The pivot is the top leftmost entry of a non-zero column, 0, 0, 0, non-zero. Now I need to perform a, what do we call it, interchange. Now that means I'm going to swap these two. All that means is that this one becomes -5, this one is 0. And the 0 swap. Okay, this is our new pivot. Everything below it is eliminated. So we're done with the top 3 rows, and we have the bottom row. And we see that the pivot is the top leftmost entry in a non-zero column, and all the remaining columns below here.